Hello everyone, welcome back to Power Electronics. Today we're going to talk about class 11. In this class we're going to talk about two things today. First thing we're going to talk about critical capacitance, and second thing we're going to talk about flyback converter. This is a new converter. So far we have talked about buck converter, buck boost converter, and boost buck converter. So this is another new converter, flyback converter. We're going to talk about how it works. And also critical capacitance is also applied to boost buck converter. So if you remember from the last lecture, we talked about critical inductance, right? So same with critical inductance, when your current, inductor current just touches zero, but it's not zero. That's the critical inductance, right? Over here, your critical capacitance is same way. When your capacitor value allows the output voltage across the capacitor, voltage across the capacitor just touches the zero, but it's on zero. That's called critical capacitance. At that point, the average capacitor voltage would be half of the peak-to-peak value. So peak-to-peak value from here to here. So your average capacitor value is half of that peak-to-peak value. So VC, average capacitor value, is half of the delta VC. Again, same as your critical inductance. If you know the critical inductance has plus minus, the 100% ripple, and same with critical capacitance has plus minus 100% voltage ripple, right? So if you want 10% plus minus 10% ripple, you make your capacitance value 10 times than your critical capacitance value. If you want 5%, you make it 20 times than critical capacitance value. That's how, if you know critical capacitance value, you can find out whatever peak-to-peak ripple you want. You can just increase the capacitance value by that ratio. All right, so this is the boost buck converter over here. So this is the energy transfer element, which is the capacitance. So we're looking at 24 volts in. So in is 24 volts and out is 12 volts, and your power is 120 watt, and we're assuming a lossless converter. All right, so that means your input current, average input current, would be 120 watt over 24 volts. It would be 5 amps, right? And your output, again, average output current would be 10 amps, right? So that is two things you need: our input current and output current. All right. So if we use the equation for boost buck converter, this is the equation over here. We're ignoring the negative sign for now. And your D1 would be 1/3 and D2 would be 2/3, right? And output power is I out times P out, average value of output, average value of current. And your load resistance, you can also calculate that, would be 1.2 ohm. So the transfer capacitance voltage VT is V in over D2. We discussed them in the class when we discussed boost buck converter. It came from this equation over here, right? So now that means your VT, transfer capacitor voltage, is 36 volts. So 24 over 2/3 is give you 36 volts. So VT is 36 volts. So now, if you come over here, your VT, that is basically VC right here for this one, is the average capacitor voltage across this guy. All right, so that's your 36 volts. If that's 36 volts, the peak-to-peak ripple over here is twice that average value, right? So that means your peak-to-peak value would be V peak, which is twice the value of this one here. So your peak value would be 72, because 36, your average value, twice of that is 72. And if we use this equation, we have been using this one for a long time. If we use this equation to find critical value over here, that critical value would be this mass. So you can see that critical capacitance value is small, because at that value, what happening across this capacitor over here, the capacitor voltage across this capacitor over here would be look like this. So that's your VC, and that's your average value VC or VT. Okay, so that's what's happening at that value of capacitor. So if you want that value, this is 100% plus minus 100% ripple right? So if you want 10% ripple, then you have to increase this one by 10 times. That would be 2.315 microfarad, all right? So that's the value here, critical capacitance value. So for buck boost, this is the boost buck, right? This is the boost buck. If you go into buck boost or boost converter, they have this equation over here. This is the equation for boost buck sorry, buck boost and boost converter, and output ripple voltage over here would be calculated by this equation over here. Delta this equation came from this equation over here. Your V equal to okay. Let me go the other. Let me do the other way around. For a capacitor, your Q is CV, right? So that came from here. So change in voltage is change in charge over C. So what is change in charge is I times delta T, because what is the current? Current is I is rate of change of charge, right? So from there, delta Q is I times delta T right here. So what is delta T again? Delta T is dt, right? This time we're using d1 is basically dt, right? So that's the whole equation here. You can really find peak-to-peak value and output voltage by using this equation for a capacitor. Okay. So now, for the buck boost and boost converter, this is your critical capacitance. For buck converter, this is your critical capacitance. For most, if you're not using capacitor as your energy transfer element, that like boost buck using, if you go here, boost buck using the capacitor as your energy transfer element, right? If you're not using a capacitor as energy transfer element, like buck boost, boost converter, they don't use capacitor as energy transfer element. They use inductor as energy transfer element. In that case, critical capacitor value is not that important. For example, if I look at the buck converter using this equation over here, right? You see that if your inductor large enough, let's say 100 microhenry and D1 is 60%, and F is 100 kilohertz, your C value comes this one here, very, very small value. So that's what I'm saying. If you're using inductor as energy transfer element, your capacitor value, critical capacitor value is not that important. So now, for the buck boost converter, we use an inductor as an energy transfer element, and that's also a element that shares input and output current, right? Because this is indirect converter. In that case, how much energy inductor can store is half Li squared, is very similar to half CV squared. And if we now split this inductor in two or more, then we'll get this one over here. So we can add all the energy stored in different inductor together to find the total energy stored in the inductor. If any inductor has a zero current, that will have zero energy stored in that inductor. So we can theoretically or also practically split that inductor over here to make multiple inductor. So one way to do it is this here. So we have one inductor, we just split it two, right? So then what is dot here? What is the dot thing doing over here, right? So dot convention is that dot means both sides, if you have a dot, they have the same polarity. That means if this is a positive polarity here, that should be positive here. And if this is a negative polarity here, that also have negative polarity here. So dot means they have same polarity at all the dots, right? So now with that, let's see how can you do that different dot. So let's see this one here. If you see that this is a positive current going in, right? It's producing a source current going in, and here is current going out this way. That is positive. So it's going to the load, right? So that means dot is here. This is dot here at this point, and there's a dot here at this point, right? Now, if I come over here, the winding changes. We can change the winding as we want. So this dot is still here, but this time dot is right here. Can you see that? So that is the dot convention. If you change the winding, and your dot position changes depending on the winding. So what is flyback? Flyback means that when your secondary winding the diode, if we go back here, there's diode here, right? So this diode will fly back or start conducting when secondary output inductor coil voltage flies back as input switch turns off. We're going to talk about the bit. So when the input switch is off, then secondary switch, which diode, starts conducting, because this conductor will make it conduct. Let me tell you this over here. Let's see that when this one is positive and this one is positive, so diode cannot work because it's reverse bias, right? But when this one becomes negative, this become negative, right? That's become negative means diode becomes forward bias, and right, then it starts works, right? So that is here is flying back to work. That is a flyback converter. So now, as you know that we can change our dot. So if we put dot over here and dot over here, so this is positive, this is negative, right? So when this one is working, this one is not working, right? Right? Sorry, positive. This is positive, this is positive. So that means this is negative here, right? So then this one, when this one is conducting, when this one is conducting, this one is not conducting. And but when this one becomes negative here, when this one becomes negative here, this is become negative, this is become positive. That means this one's working. So that is switch 1 is working, switch 2 is not working, and so on. So that is the flyback converter, right? So now what happened by doing this, by changing this dot here, your output voltage doesn't have a reverse polarity anymore. So that is the flyback converter. It's basically a buck boost converter. We fixed our polarity and also added insulation in between input and output. So this is one of the circuit out there, all right? This is one of the flyback converter from linear technology. One other thing that, as I can use transformer, so if I have the one primary here and I have multiple secondary, so each of the secondary will give me different output voltage depending on the transfer ratio of the inductor. So that's what is that within flyback converter you can have multiple DC output from a single DC input. So that's one of the beauty of the flyback converter. You have multiple output. So flyback converter, we normally use them around 100 watt converter. Your EMF induced voltage in a coil is directly proportional to frequency, and frequency is directly inversely proportional to the size. So if we use higher frequency, your converter size, your basically transformer size goes smaller and smaller, and your converter size also goes smaller and smaller. So higher frequency converter, low power flyback converter is a good candidate. So now, what is the inductance in a coil? Inductance in a coil depends on this equation over here. So N1 is a transfer ratio for side 1, L is the length of the coil, and mu is the permeability. You heard the term before in physics, permeability, right? So that's the magnetic property. Higher the permeability is better the magnetic materials, and H is the cross section area. So that is same applies to the side 2. Then if I take the ratio, this is the ratio here. So you can basically change. You can basically refer inductors from one side to another side. It's called equivalent inductance. You can take it from one inductor from one side and refer to the other side. All right. So this will show you how flyback converter emerge from the buck boost. This is the buck boost converter here, right? So now we are taking this one, is splitting over here, right? So it's still not separated, that's split it. Then you separate them, right, over here, but still the polarity did not change yet. But second one, we change the dot here, then polarity get corrected, right? So that's the flyback converter. This is the flyback converter from the buck boost converter. Fly back, and this is the buck boost, right? So then it's still something missing here. We're going to get to the next one because we're assuming that our transformer is ideal, but no transformer is ideal. So we're going to get to the next one. So over here, now you can see that there's a third coil over here. We call this magnetic core. Okay, this is magnetic core. Magnetic core. Why it is needed? Because without magnetic core, we cannot produce flux. That's the main job for that core, is to produce flux. If you have some material that has infinite amount of permeability, you can produce flux without current, but in real, you need some current to produce flux. That's the magnetic core Lm. So this is my flyback converter. Now, when switch 1 is on here, so switch 1 is on, switch 1 on, right? So this is positive here, this is positive here, right? And this positive over here, negative over here. Then negative will make this one reverse bias, so that's off, right? Off. So then your current going through this one here. This current has two values now. Is current going through the magnetic core plus current going through the primary coil, right? So then when you turn off switch 1, but this coil is a inductor, it can still push the current in the same direction, so current will go this way now, right? So that means this side makes this side positive. This side positive means this side becomes negative, right? This is dot here, right? Dots, that means dot becomes negative. So other side becomes positive. That will make this diode forward bias. So diode is conducting, so that will serve, that is providing current to charge your capacitor and also output, right? So that's how it works. So this is the input current here. Input current, two things. You have initial value, then you have a ramp to go up. This is, and you got the peak because inductor. Then and when switch, this is the switch 1 is on. So switch 1 is on. And when switch 2 is on, you get output current here. So switch 2 on, right? So and so on. So that is how it works. Let me refresh it over here one more time. So when switch 1 is on, you have this positive here, and this negative, that makes inductor reverse bias. So you got the current over here, and no current conducting through the diode. And at this time, actually, your capacitor is supplying the output. All right. Then when switch 2 is off, then look at here. Your this is now negative because your current going this way here. So this is become like this is positive here. This positive, this negative over here, that makes also this negative, and this positive. This positive will make your diode forward bias, and then your diode conducting. So now your inductor supplying the power to the output, right? Okay, so there are some equations out there. This is the equation for buck boost, the same equation for flyback. Only you have now this turns ratio out there because you have N1 N2 turns ratio, and same with your current over here. So your peak to peak value right here, peak to peak value, right, is depends on your peak minus initial value, right? Peak minus, that also comes to this equation here. This equation, if it came out VL L di dt, right? So your VL is V in at this moment, right? So that equation right there, so you can convert that to find delta IL, all right? Then your output input current would be peak current be related to your related by your turns ratio. Then your input average current could be calculated by this one here. So D1 is the D ratio for switch 1, and also your peak current, just peak current, would be initial current plus the ripple right here, plus the ripple. So initial current plus the ripple will give you the peak current, right? And this is called magnetic reluctance. Is very similar to resistance for electrical circuit. That also be calculated by this equation over here. And this is the initial flux, and this is the peak flux over here. So peak to peak flux will be calculated by this one here, right? So these are the equation to analyze flyback converter. We're gonna do that in the class. We're gonna go through some problem and do some math to understand flyback converter design. So this lecture is just to give you initial theoretical background on flyback converter. So we're going to solve problem in the class.